Last week we start to we learned something about the scientific notation. I hope you still remember, and significant figures precision, and how are you going to do the addition, subtraction, multiplication, and subtraction, right? Division using the significant figures. And also you need to validate the results, right? So there are a few ways to validate the results. I hope you remember. And also you need to know how to judge the range, the degree of the scattering using the range or sample variance or sample standard deviation. Okay, so this is the things you need to know. Once you got data, this is a raw data, right? Xi is the raw data. And for example, there are 10 data. So you need to know the range of the data from maximum to minimum. And you need to know the mean of the data. So you take the average, right? And you also need to judge how good is the data. So we use sample variance and standard deviation. So as a result, you can represent your data like this: x equal to x mean minus plus error limits. The error limits can be a one standard deviation, two standard deviations, three standard deviation, or it can be a range, okay, to represent error limits. Right, so this is what we learned last week. And today, we are going to move to a new topic, which is the section 2.6, dimensional homogeneity and the dimensionless quantity. So what is dimensional homogeneity? I'm sure you all know this equation: E equal to m mass times the speed of light squared, right? So this is Einstein's 1905 formula: E equal to mc squared. So why you think this equation is right? Why you think it's right? Okay, the reason is that one way to judge this equation probably right is using the dimensional homogeneity. What does this mean? The dimensional homogeneity tell you that the dimension on the right will equal to the dimension on the left. So as you know, the mass, this dimension m is the dimension is mass, right? And c the speed of the light. So that means the speed, the dimension is speed. So it means what? Length divided by time, power 2, right? So this is the dimension on the right. And dimension on the left is energy. So you know what's the energy? What's the dimensional energy? The dimensional energy is force times acceleration, right? So you put a unit of the force and the acceleration together, and you will get something like this. You get something like this. This is the mass times length divided by time power 2. So as you know, the dimension on the right and the left will equal to the dimension on the left. So this is what we call dimensional homogeneity. So this equation is probably right because it's dimensional homogeneity. You know that? So I hope you understand. So there's a little bit detailed description about dimensional homogeneity. Is that this is another equation. So equation U equal to U0 plus G is gravity, right? Times time. Okay? So why you know this equation is right? Because dimensional homogeneity. As you know, that is Newton's law of the motion. So V equal to V0 plus A is acceleration times T. So as you know, V is what? Speed, or we call velocity. So it's the length divided by time. And then V0 is the initial speed, right? So as you know, V0, the speed is also the length divided by time. How about G? G is acceleration. So you put G acceleration is this and the time. So as you know, on the left hand side, this is the m divided by time, right? This is length divided by time, and plus this is, as you can see here, is the length divided by time. So this is called dimensional homogeneity. Okay, so every valid equation must be dimensional homogeneous. That is all additive terms. This is additive terms. On the both sides of the equation must have the same dimensions. Okay. So there's a little bit is descriptions. So what happens if I say, well, professor, what happens if we have the same dimension but different units? So this t represent the time, right? So can I use minutes here instead of second? Yes, we can, because what? If you have a conversion factor, you can convert minute to second. So as long as the dimension is the same, it doesn't mean it need to be unit, the same unit. Okay, different dimension but same unit. Sorry, different unit but same dimension. Okay, so valid equation is the dimensionally homogeneous. Okay, all the valid equation need to be dimensionally homogeneous. However, for example, like this is correct. However, the equation which has dimensional homogeneous is not necessary to be a valid equation. Why? Because, for example, this equation, 1 meter equal to 2 meter. This is dimensional homogeneous. But unfortunately, 1 meter doesn't equal to 2 meter, right? Why? Because different value. So it just tells you that if this equation is dimensional homogeneous, it doesn't mean this is the valid equation. This is the example. Okay? Right. So next term is called dimensionless quantities. Dimensionless quantity. Let me show you one equation. This is the what is dimensional quantities? Like 1, 20, 1.5. There's no unit. There's no dimension. So you don't know one represent 1 second or 1 meter or 1 gram. You don't know because there is no unit. So this is what we call dimensionless quantities. Dimensionless quantities. Okay, so for example, this is a ratio. 3 meter divided by 5 meter. The ratio is 0.6. So it's 60%, right? So you don't know what is this. It can be 3 meter divided by 5 meter. It can be 3 seconds divided by 5 seconds. So this is what we call dimensionless quantities. Dimensionless quantities. Okay, so the 6 seconds divided by 10 seconds. Okay. Okay, there are some others. And this is important. I want you to remember this because when you find an equation which you don't know, and you want to find out the physical meaning, and this is important to let you find out what's the physical meaning of that equation. So this is the example is exponent. For example, x power 2. This 2 is dimensionless. You can think that meter times meter, like meter square. But square doesn't mean has no unit, has no dimension. So 2 is dimensionless. And also transcendental function. Transcendental function tell you that log, exponent, and sine, this kind of sine cosine. This is a dimensionless quantity. I want you to remember this. And also the arguments of the transcendental function. For example, sine, the sine is the dimensionless quantity, right? So the sine x X is a is a dimensionless quantity. Okay, so these three are important. I want you to know this. So once you do some kind of dimensional analysis, you will find out what's the physical meaning of the unknown symbols. So I'm going to give you an example here. Okay, so this is called Reynolds number. If you are second year or third year of the chemical engineering in the chemical engineering department, I'm sure you notice this is Reynolds number. The Reynolds number is equal to diameter times the velocity times the density divided by what? Viscosity. And R is a dimensionless quantity. That means there is no dimension. Okay, so if I want you to tell me what's the dimension of viscosity, can you tell me? What's the dimension of viscosity? Can you tell me? Or if I ask you on Wednesday in the question of Kahoot, say, please tell me the viscosity of the dimension of the viscosity. I give you 4 choices. Can you tell me which one? And of course, I will tell you Reynolds number is a dimensionless quantity. Okay? So actually, the physical meaning of the Reynolds number is inertial forces against viscous forces. The initial force means this is an object. This object want to move forward. This is called inertial forces. And there's one force which want to pull this object back. So these two forces against each other. So inertial forces against viscous forces. And the number you get is called Reynolds number. So the initial forces is higher, then Reynolds number will be higher. The viscous forces higher, then Reynolds number will be lower. Okay, I'm sure you will understand this number very well when you go to the second year. But I don't want to tell you too much story about this. But what I want to tell you is that, this is Reynolds number is the dimensionless quantity. So the unit, for example, the unit of the diameter is centimeter. Velocity will be centimeter divided by second, right? And the density will be gram divided by cubic meter. So as you know, if this one need to be dimensionless, so you will know that the dimension of the viscosity will be gram divided by centimeter times second. So this is the unit of the viscosity. That's the answer. If I give a question of Kahoot like this will be the answer for the unit of the viscosity. Okay? So, and this one we call dimensionless quantity, as I just showed you. And these are called dimensionless group. Dimensionless group. Okay. I hope you. Important thing is this dimensionless quantity. Okay. So there are many dimensionless groups, dimensionless quantity, like Reynolds number I just showed you, right? And then ratio I just showed you, meter divided by meter. And this pi is dimensionless quantity. There's no unit of pi. It's a kind of ratio, right? Ratio. Okay, so this is an example in your textbook. This equation is K equal to A times exponent minus B divided by CT. So this is equation. And here, I tell you that A is 1.2 times 10 to 15th. And B is 20,000. C is 1.987. So I give you the numbers of A, B, and C. But you don't know the physical meaning of A, you don't know the physical meaning of B, you don't know the physical meaning of C. So you need to find out the unit, and then so that you can understand the physical meaning of these symbols. Okay? So here I tell you that, wow, K, the quantity of the K is mole per cubic centimeter times second. And please tell me the unit of A and unit of here 20,000. This is the car per mole. Okay, the unit is car per mole. Calorie, right? Calorie per mole. Okay, and T is the unit of T is temperature, the Kelvin. So here I give you three dimensions. One is K, one is B, right? One is T. So the question is, I want you to find out the quantity of the dimension of 1.2 times 10 to 15th. Or I want you, and also I want to find out the unit or dimension of 1.987. Can you do this for me? In your midterm exam, probably I give you this equation, and you need to tell me two answers here. So as you know, exponential, this is dimensionless, right? As you know that. So that you know that 1.2 times 10 to 15, the unit need to be the same as this unit, right? Right? Okay, because this is dimensionless. Exponent is dimensionless. Okay, so 1.2 times 10 to 15, the unit of this number needs to be this one. Okay, it's easy. How about this one? 20,000. The unit of 20,000 is calorie per mole, and need to be equal to what? 1.9 times the unit of 1.987 times Kelvin. So as you know, you just move this to this side. You know the answer of the unit of 1.987. Okay. Okay. So the conclusion is that dimensional homogeneity, dimension on the right equal to the dimension on the left. Okay. So there's a sum of the dimensionless quantities like this. I highlight in yellow color. So here, these dimensionless quantities. Okay. I just give you a little bit information about Reynolds number. If you are a chemical engineer, you need to know what is Reynolds number. Otherwise, you are not qualified as a chemical engineer. Okay, so Reynolds number is a qualitative behavior of a fluid flow over a cylinder depends on a large extent on Reynolds number. This is one of example to express Reynolds number. You have a cylinder bar, and the water flow from the left to the right. And once the water flow met this cylinder bar, some of them will goes up, some of them will goes down, right? So you will make a pattern. It depends on the speed of the water. If it's very fast, you found different pattern. If it's very slow, you found another pattern. So similar flow patterns often appear when the shape and the Reynolds number is matched. So once I tell you the Reynolds number of this situation, you'll realize what kind of pattern you can get. As I told you, Reynolds number is inertial forces against viscous force. One goes front, one pull it back. So if the Reynolds number less than 1, much less than 1, that means what? The pattern will behave like this, very slow. So if you increase the Reynolds number, the pattern changed. For example, if you see a cartoon like this is the Reynolds number is more than 90. So it becomes like this. Some of the flow water goes up, some water goes down. And if you increase the Reynolds number to a power to 10 to power 4, 10 to power 5, you will flow very fast. Okay, it tells you the different patterns. So you don't need to remember this because this can be a cylinder, it can be a ball, a sphere, or it can be a tube. So it really depends on different shapes. So you will define different, you will get different definition of the Reynolds number. Okay? And there are many dimensionless groups in terms of physics, mathematics, aerodynamics, chemistry, and optical studies. This is refractive index. Okay, there are many dimensionless groups. Just here, you don't need to remember this, just here, just for your information. Right, this is the summary of the chapter 2. I will skip this first. Okay, so let's move to the section 2.7. The section 2.7 is that how do you represent the data and how do you do the analysis of the data? Right, so you might say, well, Professor, you already told me how to do the analysis of data because like this example, I do 10 times experiment, I got 10 data. And I know the mean of the data and I know the error limits. So I represent the data like this. This is correct. Okay, this is one of the methods. One experiment you do 10 times. However, there are 10 rounds. You can do 100 rounds. Okay. However, there are another type of the data representation. For example, this is a salt water, sodium chloride. You put salt into the water, so the salt dissolved. It becomes sodium cation and a chloride anion. Okay, so if I want you to measure the concentration of this sodium chloride, so how can you do that for me? You might say, well, Professor, this is easy. There are many instruments yet we can do. Like we use thermal electrical conductivity to measure the concentration of the sodium chloride. Or we can use the absorbance, the light absorbance to measure the concentration of sodium chloride. And we can use titration. This is basic chemistry. You can learn this in a basic chemistry lab, right? So this is the value of the titration. Okay, so there are many ways to do it. So let's use the example of titration. Is that if we fix the x, the concentration of this, and we get y. So this is the fixed concentration, and we get y, right? So we can get something like this. We do 10 times. We do 10 times, so we can get numbers. Again, we get the one you just know. However, there's another way if we want to change the concentration of sodium chloride in this solution, aqueous solution. Then we might get something like this. Because X is the concentration, right? We change the concentration. We use titration to get the concentration. So we get Y here. We change the concentration, we get another Y. So you will get a plot like this. A plot like this. So you know how to express these data using this line, right? So how are you going to express a line using this data? Okay, how to estimate the value of y for a value of x? For example, you know that if we do the, and then how to find a curve which represents this data. Okay, here is an example. You know, if I have a concentration of 9 and I got one data here, right? So I do the titration, I got the data here. So I know what's the y. And also I know if I increase the concentration, which is 10, and I got another y. This is for sure. This is for sure. There's no problem because you do the experiment and you know that. However, if I ask you, please tell me the value of y if x reach to 9.5. So which one you want to tell me? Which point you want to tell me? You might say, well, it must be between these two. It must be somewhere around here. Right? You tell me this answer. Okay, this is correct. This is not 100% right, but it makes sense. It makes sense. You might say, well, Professor, it might be not between these 2 points. It might be somewhere here because I know the tray, it looks like this. It looks like this. So it might be somewhere around here. And then y will be different. So this section won't tell us, we want to find out this line using a mathematical equation. So you can do interpolation or exploration method using 2 points. However, it might be more scientific approach to get this line, to represent this data, right? To represent this data. So 2-point linear interpolation, like as I just told you, you have 2 points, right? Or you can just draw it as you like. You might say, well, Professor, I don't like this line here because I feel this is not correct. I might want to draw a line like this, which is different. I might want to draw a line like this, which is different from this one. Yes, it is possible. Okay? Or you might use mathematical curve fitting to find this line. Okay, so here the most simple way is 2-point linear interpolation. I'm sure you learned this when you are in junior high school. 2-point linear interpolation is that you have 2 points. 1, 2 here. And then I want to find out what is the value on this line. I'm sure you know that, right? So if you use this equation, you point an unknown here, and you can find out equation like this. In the end, you got y equal to a times x plus b. So you know a is the slope, b is the what? Intercept, right? B is intercept, a is slope. I'm sure you know this. Right. So 2.7b is fitting a straight line. So again, if you have this, something like this, and you find out 2 points, this point and this point, and if you draw a line, this line can be easier to represent these points. So fitting a straight line, you can just draw it as you like, as long as you don't draw something like this. You don't draw something like this. You draw it very close to these 10 points, 10 data. Okay? So draw a calibration curve here, here, and you find this line. And then you find equation, right? If you get this, and you find that's 2 points, you got the equation. and you can get y equal to a times x plus b. However, there are many statistical techniques. Statistical techniques, linear regression, the method of least square. Okay, there are many mathematical models you can use. But we don't have time to tell you this. You know, now in Excel, you can just put the data in and Excel will do the computation for you. And easily to give you answer. But important thing is you need to know what's the meaning of this method. That's very important. Right. So here is the calibration data. The example 2.7 flow meter calibration. So does anybody know what is this for? You know, as a chemical engineer, you need to know how to measure temperature, how to measure pressure, how to measure flow rate. It can be liquid flow rate, it can be gas flow rate. And this is the tool you use to measure the flow rate. And this kind of design, we call it rotameter. Rotameter. Let me show you. So the rotameter, it looks like this. This is the float. The float. The flow go from the bottom, and flow will goes up, right? The flow will goes up, and when the flow goes up, it can be water. Let's say water, and this water will push this flow up, and you can, if the flow goes up, you can see the reading. For example, this is 5. This is the number. This is the number. Volume. So where is the unit? Units here. GPH. This is gallon per hour. Gallon per hour. It tell you what? Volume per time. Volume per time. Gallon per hour. So you know this is if flow push up to here, this is 5 gallon per hour. Flow rate. Flow rate. If the flow gets stronger, this floater will goes up to higher position. For example, if the floater goes up to here, that will be 15, right? This will 15 gallon per hour. And then the flow go out here. So this is a regulator. You can just tune the flow rate. If you want to make it higher or make it lower, this is the valve. The valve. You can just change the flow rate. Okay, so let me show you the real example. This is small stuff. The flow rate meter can be very big. It can be very big, right? And here, because this is small, you know, it's small, very small. I don't know whether I have. Presenter. Does it work? No. Can I see? Right. Seems doesn't work. Let me see. Is this set up? Unfortunately, it doesn't work. Right. I might show you next time. So this is a kind of flow rate meter, and you know this is a tapered. We call it tapered metering tube. So it's big, it's small in the bottom, and big on the top. So the flow will push from the bottom to the top. And this because of gravity and the flow, the force of the flow, this the floater, or we call float, will stay in somewhere. Depends on how strong is the float of the flow rate, right? How fast is the flow rate? So you will stay. If the flow rate is strong, it will goes up, right? And you got a reading, higher reading. If the flow rate is low, you got lower reading. Okay. So this is the flow rotameter we need to know. So once we have a rotameter, and you know this is the float, and the float goes up, and this is reading, right? And what is this? SCFH is called standard cubic feet per hour. So this is feet is a volume, hour is time. So this is the flow rate, volumetric flow rate. So the volume divided by time is a kind of flow rate. Okay, so once this float goes to one, here, that will be 0.1 standard cubic feet per hour. If this goes to here, that's 0.4 standard cubic feet per hour. Okay, so this is how a flow rate, a rotameter works. However, sometimes the reading is not correct. Or if I say, well, I want you to change standard cubic feet per hour to standard cubic meter per hour as SCMH. So you had to do the calculation, right? You have to do the calculation. How about if we have a reading matched to the real flow rate? That means we need to do the calibration. So we don't know this is right, this is correct number or not. That's why we need to do the calibration. So how can we do the calibration? So this is called floating indicator, okay? Floating indicator or floater or float. And this is what we call reading. So if the reading is not correct, then in that case, we need to do the calibration. So here, in the case here is we have the gas in and we have gas out. Gas out. Or it can be a liquid in and liquid out. Okay? In this case, it's gas in, gas out. So what are we going to do the calibration? To calibrate these numbers. This is called bubbler. Bubbler. Bubbler is like this. Bubbler is like this. So we connect the gas out to this bubbler. And we have bubble. It's it kind of soap water. Soap water here, and we push, and the bubble will come out. So this is the line of bubble. And then air will push this bubble up. So if we know the value of this from here to here, for example, 50 milliliter, and and then we know this bubble run from here to here takes 10 minutes, 10 seconds. So 50 divided by 10, that will be the flow rate, right? That will be 5 milliliter per 1 minute, right? For 1 minute. Okay, something like this. So in that case, we will know this is read. For example, if the flow come here, will be know 0.1 equal to what? 5 milliliter per minute. Okay, so we have X and Y here. I don't know you understand me or not, but let me show you. This is called bubbler. This is the bubbler, and you have gas in and gas out here. So I know there's a label here. This is the 0, and then this is 50. So from here to here is a 50 milliliter. So I have water and soap water here. So I push here, and then the bubble will come out, right? So when bubble come out to here, and the air will push to here, air will push this bubble. So bubble will goes up. So I have a timer. So I start to tick from 0, and then bubble will goes up, and then eventually reach to 50, and I stop the timer. So I know how long does it take from here to here, right? For example, 10 seconds. So from here to here takes 10 seconds, and the value from here to here is 50 milliliter. So what's the flow rate? 5 milliliter per minute per second, right? 5 milliliter per second. Okay, so, and then if I have a reading which is 0.2 at this time, so I know 0.2 will related to what? 5 milliliter per second. Okay, so I will have many points. I will collect 10 points. Because I change the regulator, I get different speed. So speed of bubble will be different. So I can get 10 data, right? I can get 10 data. Let me show you a video. I asked my student to do this video. So this is called bubble calibration experiment. So you can see something here like this. So this bubble I just show you. And this is a rotameter, right? This is bubble I just show you, right? As you can see here, can you see that? This is the bubble, right? Bubble from here. I have timers. I start, and it goes up. This is 10 milliliter, right? From here to here. So this is timer. So I was stop. Oh, sorry. It seems it goes to the 20. So time goes by, and this goes up, bubble goes up, and then, okay. So, for example, just show you that if you had to, here is that you got 20, right? And the time is 20 seconds, right? 20 seconds. 20, right? And 24 seconds. So you know the speed, you know the flow rate. Okay? So this is what we call calibration. So what I want to show you here is that you do 5 times experiment. So you know the reading here, this is X, is 10, 30, 50, for example, 70, 90, for example. And when you get the flow rate, this is true value because you do the calibration. You know that when the reading is 10, it goes to 20. When the reading is 30, it goes to 52. When reading is 50, it goes to 84.6. So as a result, you can plot reading against Y. Y is what? V over dot. V over dot means what? Volumetric flow rate. Over dot means what? In our class, over dot means divided by time. So it's kind of speed, velocity. Okay? So V is represent volume, right? So volume over dot means volume divided by time. That means the velocity, volumetric flow rate. Okay? So as you know that you have 10, 30, 50, 70, 90. Then you got 5 data. So how are you going to represent these data? If I ask you, please tell me that when the reading goes to 20, what's the volumetric flow rate? Can you tell me? Well, you might say, well, between 20 to 50. Or you might say, well, 35, something like this. But can you give me a precisely or more scientific result or scientific answer? Can you tell me this? Yes, as long as you find out this equation, right? You can give me more precise answer, which is more scientific result, right? Okay, so how are you going to find this plot? How are you going to find this? Well, you can say, well, I have 2 points. I do the plot, or I just draw by my intuitionally. Intuition means that as you like, right? Or you can do the statistic techniques like linear regression, method of least squares, something like this. Okay, so this is the one. Right. So this next section tells you that if this is not linear, this is non-linear, how can you fit the data? Of course, linear, you can find linear regression, or you can find equation y equal to ax times b, right? So what can you do that? Prediction of the data by equation. For example, if you plot like this, you might say, well, this looks like linear, so I have a line. You can do this, right? Okay, so that will be y equal to the function of x. So x related to y. That's why we call y equal to function of x. Okay, so this is linear. So y equal to ax times b. That's why all we know. However, if you got a data something like this, you might say, well, this is definitely not a linear equation. Okay, so it can be, but of course it's a function of y equal to a function of x. This is for sure, right? This is for sure. So you might say, well, this is y equal to ax power 2 times bx times c. It makes sense. But can you give me this equation according to what we just learned previously? No, you cannot. So then what happened? What can we do? What can we do is, now I'm going to show you, if you have nonlinear data, make it become linear. That'll be easier, right? So here is an example. Does anybody want to tell me the name of this course? Elementary principle of the chemical processes, right? Elementary principles of the chemical processes. Okay, so this is the time you spend for a day to play computer games. Okay, and this is the score you can get. This is the final score you can get for this class, for this course. Okay, let's assume something like this. So for example, if you spend 12 hours within 24 hours, that means you spend half day to play game. I'm sure the final score of this course will be very, very low. Let's say 15. Of course, you fail. I'll see you next year, or next year, or next year, right? Okay. However, you know that, and you think, well, Professor, I want to reduce the time of the playing games. Okay, so you reduce to 6 hours. That means quarter of the day, right? One day, 24 hours, right? So you have quarter of the day you play games. That's also heavy. You are brave, right? As a college boy. Okay, so the final score you can get is 30. Again, I fail you. I'll see you next year or next year, right? So you say, well, let me reduce to 4 hours. Can you do that? Of course you won't. If you can, right? The scores is not satisfy you. You still fail. So the maximum is if you play 3 hours. Okay, that will be 0.125 days per day. You pass. Okay, if you play 2.4 hours, you got score of 75. If you only play 2 hours, you got score of 90. Then here I want to ask you, You might say, well, Professor, can I play 1 hour? What's my final score? Can you tell me? If I play 1 hour only a day, what's the final score? You might say 95, 99. Which one? Do you have a mathematical model for this data? Okay, that's what we are going to learn here. So when you plot, this is the x, this is the y, right? So when you reduce the time of the playing game, you increase the score of this class, of this course. Can you do a mathematical model for this line? No, you cannot. And do you remember I told you, if this is not linear, make it become linear. So you are very smart. You think that, well, Professor, can I reciprocal of this x? So if 0.5, that means 2. 0.25, reciprocal of 0.25, that means 4. So when I have reciprocal of x, I got 2, 4, 6, 8, 10, 12. So I replot this data with this data. Now this data to this data. This data to this data is this one, right? This data to this data is this one. And I plot something like this. We'll say, whoa, bingo, I got linear equation. Can you do that? Of course you can, right? So if you do this equation, I ask you, if you want to get a score of 90, how many hours you play game? Okay, can you do that? So this is the equation now you need to know. It's y equal to a divided by x times plus b. This is reciprocal x is x prime, not be the same, right? As long as you find out a and b, then you can tell me how many hours you play and what's the score you can get. Or you can say, well, I want to get 70 in my final scores. How many hours of game I can play, right? Okay? I don't want to waste your time. I'm sure you can find out this by yourself to get A and B, and you can tell me the answer. So the point here to tell you is that if this is nonlinear, make it become linear, and you can get the answer. So any nonlinear equation, x and y, to make it become linear. And of course, the quantity will change, right? A will become quantity 1, B will become quantity 2. That means y will become quantity 1, x will become quantity 2. It doesn't matter, right? Okay, so could you tell me what is, for this one, what is quantity 1 and what is quantity 2? Let me see what is quantity. Okay, what is quantity 1? Quantity 1, y equal to ax power 2 plus b. What is quantity 1? It's y, right? Quantity 2 is x power 2. Right? Okay, so you need to plot what? Y here. It become what? X power 2 here. You've got linear equation. So how about this number 2? How about number 2 here? It's y power 2. And why is this is reciprocal of x. Right? So quantity 1 and quantity 2. How about this one? Again, right? Plot reciprocal of y, and this is x versus x plus 3. How about this one? Sine y again, right? Sine y. Easy. So in order to get equation, this is the simplest way to find out the equation, to do the mathematical model. How about this one? Number 5. It looks not easy, complicated, but however, if you reciprocal of this equation, you got something like this. So it looks clear for you, right? Again, this one is the same. It looks complicated in the very beginning, but if you do some of small trick, move the numbers around between equal equation, because between this symbol, you can get something like this. Okay. Right. So summarize the procedure. First, step one, if it's nonlinear data, change to the equation like this one. F function of xy times g function of xy times b. So it can be g function of xy, f function of xy. So quantity 1 will be function of xy, quantity 2 will be function of gf or g of xy. Okay, and then start to do the calculation. Again, you do the 2 points. You pick up 2 points in this equation, right? And you do the linear, you can make it as y equal to x plus b. It can be, or you can draw a line if you like. You can do linear regression or least or another mathematical model. Okay. Right. So another example here. This is the m over dot. What do you mean? Do you remember I told you m over? What does it mean? What does this mean over dot? Over dot is time, right? Time. So it's mass over time. What does that mean? Mass flow rate. Previously, I told you that V over dot is volumetric flow rate, is volume divided by time. So we call it volumetric flow rate. And this M divided by time means what? Mass flow rate. Mass flow rate. And mass flow rate is related to, what is this? Temperature. If the temperature goes higher, the mass flow rate goes higher. Okay? So when you draw a plot like this, T here, 20, 10, 20, 60, 80, you got mass flow rate like this. Unfortunately, this is not linear. This is not a linear equation. So you need to make it as a linear. Can you do that? If I don't tell you this, I don't know whether you know or not. Of course, in your midterm exam, if this question shows up, I'll tell you there's a reason to believe the mass flow rate vary linearly with the square root of time of temperature. Square root of the temperature means what? T to 0.5. This is the square root, T square root. So there's a reason to believe this one is linearly related to this one. And now you know how to plot the line for me, right? Can you do that for me? Okay, and as long as you find A and B, and I can ask you if the temperature goes to 90 or if the temperature goes to 40, and what's the mass flow rate? You will be able to tell me according to this equation once you find out unknown A and B. How do you find out A and B? Easy. You learn this in high school or junior high, for example. Right. So there's a reason to believe, right? This is related to the square root. So let's plot this data. Let's have a square root of the temperature. And 10 square root is 3.162. 20 square root is 4.472. 40 is this. 80 is this. So now you need to have a plot like this. Plot the mass flow rate versus the square root of the temperature. So this square root of temperature here, and this mass flow rate. And bingo, you found out this is linear. This is linear. And once this is linear, you just pick up 2 points and make a straight line. You can get A and B. Or you can use a ruler to do it intuitionally, right? As long as you find out what? As long as if you use a ruler to make a straight line, and you need to know the slope and the reciprocal, then you can get A and B, right? Okay, no problem. So in your midterm exam, if I give you an example like this, you can use mathematical model like linear regression, or you can use 2 points to find out a line, or you can use the ruler to draw a line. It's all okay in your midterm exam. Okay, so bring a ruler if you want to. So choose 2 points and calculate A and B. This is the simplest way. Okay, so here I want to tell you that the common nonlinear functions are to make it linear function, to make it become linear equation. So y equal to a times reciprocal x plus b. That's what I just give you an example, right? This is the example of what? The score of your elementary principle of chemical and engineering process, right? Okay, this is the reciprocal. This one. And this is the square root, right? Y equal to a times square root of x plus b. This is the previous example of temperature related to mass flow rate. And this is another example is that y equal to a times exponential b times b. This is what we call exponential function. Exponential function. This is a very common nonlinear regression. You need to change it to linear equation. And in this case, this is the natural log. If we use natural logarithm, okay, ln to the both sides, you got natural log y equal to natural log a plus what? Because this is exponent, right? Exponential function e will be 1, right? So you got natural log b times x. So you got something like this. And then for the y-axis, you will use what? Natural log y. For the x-axis, you will use what? X here. So here will be x, here will be natural log y. Okay? Another case is called power law. So exponential function and power law is the one here in this page you need to remember, in this slide. So y equal to a times b power x, power y. So this is what we call power law. Again, if you times natural log in both sides, that will be natural log y equal to what? Natural log a times b natural log x. So for the y-axis, that will be natural log y here. For the x-axis, that will be natural log x. Okay? Right. Do we have time? No, we don't. So I think this is a very important example for you to know, and I think I better not to talk about this now. I will keep this for for Wednesday. Okay, so that's it for today.